Okay, how's everybody doing? So, for those of you who haven't had me before, one of the things I like to try to do is make these presentations for you. The idea behind it is we can kind of have a one-way conversation, me talking to you about some of the things that we're going to discuss in class. So I've kind of pulled out some of the important or salient pieces of information from Chapter 3, which talks about ecosystem and ecosystem ecology. We'll spend a lot of time on this general topic over the course of the first couple weeks. It's broken down into a lot of different pieces. I'll pull some of the more important pieces out of the chapter and take a look at them. So one of the things we'll look at is developed versus undeveloped countries. So Haiti, for example, is an undeveloped country that has a huge issue with deforestation. I'm not sure if you remember this, but maybe about 6 or 7 years ago, there was an earthquake in Haiti, followed by a series of flooding rains and total mudslides, all these kind of things that happened there that were obviously portions of these events are not caused by humans. For example, earthquakes are not caused by humans, but we can argue that the stronger tropical storms are due to global climate change. So the reason I bring up Haiti is a great story about it at the beginning of the chapter. So here's Haiti. Haiti's found in the Caribbean, however you want to say it. It's on one island. The island, I believe, the original name of the island was Hispaniola. I think that's what Columbus or one of the explorers named it originally, Hispaniola. You can see Cuba kind of off here to the north and west. So here's a picture of Haiti from the air in the Dominican Republic. So you're seeing Haiti on the left and the DR on the right. We're talking, you're probably looking at maybe a quarter of a mile worth of land. I would think that it's kind of shocking to see that Haiti's kind of bald, if you will. There's no trees, no vegetation, whereas the DR is super lush. Obviously, this must be some type of a boundary or borderline between those two countries. So what's happening here is that in the country of Haiti, there's very little industry. There's very little natural resources. They have a small amount of tourism, but it's very, very low for the most part. So due to some of these things, the wages of people that live there are pretty low, $2 a day. And this is going back to 2012 when our book was published. So they really don't buy oil. They don't buy gasoline. You don't see a lot of people with large cars. I think it was Brendan we had a conversation with the other day in class about his vehicle gets 8 miles to the gallon. You wouldn't see trucks like Brendan's down there. You'd see small motorbikes, maybe very, very small fuel-efficient vehicles, those kind of things. Anyway, the reason that it looks like this is they cut the trees down and they use the trees to create charcoal and the charcoal to create fuel to cook with. That fuel source is kind of one of their major, I don't want to say imports, exports, but it's one of their major commodities that they make there. And we'll watch a little video on this at some point. So the charcoal is made from trees and bushes. As they create this charcoal, another issue becomes soil erosion. So now you have heavy rains. We know it's where it is in the Caribbean. It's going to rain a lot down there, and we'll get into why it rains in the Caribbean or why it rains in those southern latitudes like that. But what's going to happen is you have this lack of trees, which does not hold the soil in. When it rains, soil washes away the nutrients and minerals that are in the soil that are needed for plants to grow, then causes it to be more difficult to then grow new trees after this happens. The other thing with deforestation, it also can increase the risk of flooding, and in some areas that flood water can then be mixed with sewage, which then creates a whole other set of issues. And we'll get into that in later chapters. So here's another example. This is an example of a delta. Delta is a freshwater river of some type that then splits and diverts into different smaller tributaries. Delta obviously is a change in Latin. So a little symbol of a triangle. You can see a little triangle kind of here. I'm sure is where they get that name delta from. And there's a change in the direction of the water. The picture on the left shows a 2002 version. The picture on the right shows the same place in 2010. Notice all these little green rectangles. All these little green rectangles, I'm assuming, are farms. Right? When you cut down trees to produce farmland, one of the things that you do is you change the way the water moves. It's sometimes referred to as a watershed. So as you change the way the water moves, Now, instead of the water being absorbed and slowed down by the trees that are there, it runs right off these flat surfaces, which in this case are these farms. And you can see there's this flooding of minerals, nutrients. This is probably silt, sand that then shows up here. And so obviously, humans have had an impact on the land, which then has an impact on the rivers and streams, which then has an impact on this delta area that then dumps out into some I'm assuming some marine or saltwater bay. So anthropogenic or man-made effects, woman-made effects are very prominent here. Here's another example of it's an aerial view of a country. Not sure which country. It came out of the book. There are 1950s shows where the tree cover was in the 1950s. And as you can see, over the course of, in this case, about 60 years, I would say right here is where we would stop. In 2010, over a 60-year window, the number of trees has dropped probably somewhere by half. And this has to do with, once again, humans using the resources as a commodity, commodity being the wood, for whether it be for fire, for construction, for anything that you would use wood products for. And this is probably, this 2020, obviously we're not quite there yet. I would make the assumption that when this book was written in 2012, they took 2010 data and they extrapolated that out to 2020, expecting that this is what you're going to see in this area. And unless we have some type of healthy cutting practices, we're going to see this kind of globally. So ecosystems and ecosystem boundaries. So the two major things that are found in ecosystems are biotic and abiotic factors or inputs or outputs. Biotic means living things. Abiotic or a without life. So biotic would be all the living things in an ecosystem, whereas the abiotic factors would be things that are not alive. So you could be talking about soil, rocks, temperature, the amount of rainfall, things like that would all be abiotic factors. Ecosystems can be large or small. On the right-hand side of the screen, we're looking at a small ecosystem that, if you ever walk through the woods, you see a downed tree, there's a hole in it, rains, fills with water, and you get these microorganisms that begin to grow there. Very, very cool little small niche type ecosystem. You could also compare this to in the ocean, when the tide goes out, there are these tide pools that are left, and a lot of times you see small little ecosystems that exist for short periods of time in these little tide pools, as opposed to a larger ecosystem such as Yellowstone. You have trees, you have birds, you have bears, bison, all these kind of things there. You never know what kind of impact's going to happen when you remove one or more of these organisms from an ecosystem. There's a really cool story about it's back in the 60s or 70s, I believe. They actually in Yellowstone National Park and the surrounding areas, they removed a lot of the wolves that were there. You have a lot of, in this area of the country, you have a lot of farmers, and farmers tend to be more like ranchers, cattle ranchers, and there was a huge issue with wolves eating cattle. So the governments of, I'll use like Wyoming, Montana, Idaho areas out in our Midwest, they allowed hunters and they allowed farmers to kill wolves to protect their livestock. It's here, the livestock is my livelihood, it's how I feed my family. What happened after that is the population of wolves went down to somewhere under 100 wolves. So now you have this gene pool of wolves with only 100 sets of genes to go around, and they found that they had to create new breeding lines of wolves. So they would take wolves from one area and another area, crossbreed them to get wolves that were a little bit healthier. Because in the wild, if there's only 50, 60, 100 of these wolves left, you could have mothers mating with sons and grandsons. The wolves don't really know any better in that sense, which then can have a huge effect on that population. Now I want to say, since they've stopped the hunting of wolves, obviously, and they've done this kind of selective breeding, they've found that they've brought that population back and it's becoming super healthy again. So it's, once again, interesting how man can affect this. So one of the other things we'll talk about in this chapter is energy flow. The two ways that energy is produced in all environmental systems is either chemo or photosynthesis. Chemosynthesis was probably the dominant type of production and energy production, probably going back before the dawn of plants. And this was microorganisms, probably in the sense of bacteria, that were taking some of the raw materials that were found on the planet and using the heat and and sulfur type products that were available on the planet at the time of its inception to then create organic compounds. Photosynthesis, we've probably all heard about. We know plants do it. They're some type of a producer. It actually uses the movement of photons from the sun to generate electricity, or generate. I'm sorry, that'd be solar panels to generate. It does generate electricity in some respects, but it causes this movement with inside plants that then can drive the process of the production of organic compounds. Ironically, solar panels are based on a very similar mechanism on how photosynthesis works, and we'll get into that when we get into renewable energies. So chemosynthesis, once again, they use usually there has to be a source of hydrogen. Hydrogen sulfide tends to be the big one, or hydrogen gas. And what happens is these organisms that can live in harsh, warm, usually inhospitable places are able to turn these basic compounds and structures into organic molecules. Super rare on Earth. You only find it usually at the bottom of the ocean, around thermal vents, things like that, maybe around volcanoes. It's places that the Earth, it gives us an idea of what the Earth used to be like, because this used to be the dominant form of synthesis. And as the Earth cooled and more light was available and we generated an atmosphere, photosynthesis became kind of the big one. So photosynthesis is a pretty straightforward example of it. There's three things that go in, two things that come out. Sunlight drives the process. It can also be regular light from a bulb will also drive the process, but sunlight drives the process for the most part. CO2 is an input, water is an input, and when you take sunlight, CO2, water, and the presence of the right enzymes in plants, you get oxygen as a byproduct or a waste product, and you get glucose as a product that the plant uses and stores that energy. So think of it as like you're charging your cell phone at night. You plug it into the wall. That would be the source of the energy, or the sun. Your cell phone would then take in the batteries. There are chemicals in the batteries that then are excited when the electricity hits it, and at the end of the day, you're storing. You're taking energy from one source and storing it somewhere else. That would be kind of like the glucose of it. Eventually, you turn your phone on, you run out of it. So in order to recharge it, you have to plug it back in. Same thing happens with plants. Plants basically create glucose for themselves. They're not creating food for us. They're creating food for themselves, and that food then is used as a source of fuel when there's no sun. Ironically, over the course of evolution, plants have evolved to have different types of leaves, different types of fruits, different types of stems. All these evolutionary pieces probably co-evolved with animals. For example, think of apples. Apples are super tasty. Well, they're tasty because the benefit of the apples being tasty is that animals will eat those apples, consume the seeds, move from one place to another, and disperse the seeds as they move. So you think about a deer going to an apple orchard and eating a couple apples. They're not picking through the seeds. They're eating the apples, swallowing the seeds. Deer trots off into a different direction. Deer relieves themselves and has a little deer poop. And in the poop comes the seeds. And those seeds then now have a source of fertilizer from the feces of the animal. And that's a way of dispersing your seeds. So there's a lot of symbiotic relationships here, which is really kind of cool. So at some point we'll have a conversation about you'll work in groups of two. You'll each get a choice of countries. You'll pick a developed versus an undeveloped country, and you'll look at how the abiotic and biotic factors in those countries drive how they do things. For example, go back to the island nation of Haiti. Haiti does not have a lot of natural resources. They don't have a lot of abiotic factors that are things that they can use to manufacture or create energy for themselves. So they use those their resources in such a way that has had a detriment to their country. You can say the same thing about the U.S. We have a ton of natural resources. They tend to be packed in different areas depending on the resource you're talking about. For example, coal seems to show up mostly in the West Virginia, the Carolinas, and Pennsylvania. That's where our coal production happens. We look at oil production, Alaska, Gulf of Alaska, mainland Alaska, Gulf of Mexico, Gulf of Texas. Those are places that our oil reserves are. So we still do the same kind of thing. We have a huge impact on the biotic or living factors in our own ecosystems based on how we treat our abiotic factors. For example, you guys probably remember 2010, so years ago, there was the Gulf of Mexico, there was the oil spill. Not the Exxon Valdez, it was the, oh boy, there was a movie with Mark Wahlberg. Now I'm drawing a blank here. Deepwater Horizon. So Deepwater Horizon was an oil rig platform that there was a break in the oil pipeline. That oil then was just spewed out of the bottom of the ocean and had massive. So once again, the abiotic factor having huge impacts on marine life, whether it be marine mammals, fish, organisms that live near the shore that then rely on fish and what have you, seabirds, those kind of things. There's a huge impact there. And we'll move into the other pieces once again as we go. The last couple things here, primary versus gross productivity. I always like to use the analogy of if you have a job, you have a paycheck, you have a gross and net pay. Gross pay, let's say you work at Dunkin' Donuts and you make $12 an hour, work 10 hours, you've made $120. So you've grossed $120 of income. However, you get your paycheck and the state takes money, the federal government takes money, you pay Social Security taxes, maybe you have like a union, maybe you have health insurance. Next thing you know, that $120 worth of gross income maybe works out to be $60 at the end. So the same thing is true about productivity. Plants or producers have something called primary productivity. They're the ones that are making all the energy for us. There's gross versus net. Gross is all the energy an organism or a plant can make by itself. So if we used a tree, let's say the tree can make 100 units of energy. That's its gross primary productivity. If you have 100 trees and each one's making 100 units of energy, you've made what? A quick 10,000 units of energy. Net productivity is how much that tree needs for itself. So if a tree is making 100 units of energy and maybe needs 50 units of energy for itself, there's 50 units of energy left. That is the net productivity. That's how much is put back into the environment for the use of other organisms, such as herbivores. So here's another quick example of it. So of all the light that comes, or all the energy that comes from the sun, we only use about 1% of it. The rest is bounced back into space or totally unused. And that 1%, we're not talking about people having solar panels on their house. We're talking about things that produce energy. Only 1% of that solar energy from the sun is actually producing energy that can be then used in biological systems. I mean, it'd be amazing if we could bump that up to 1.5%, 2%, 3%. We would really find a great way to kind of have a positive impact on the things that we do. I think you're going to see a lot more of this, using more of that solar energy through the use of things like solar panels, and we'll get into that more when we talk about renewable energy. Anyway, so they're talking about, in this case, they're taking that 1%, pulling it off as the yellow line of the gross primary productivity. So, and according to this, they're saying that, 60% of that is lost due to respiration. So in other words, they're breathing out 60% of the energy that they create, and 40% supports the production of growth and reproduction of producers. So really, of that 1% that's being used, only 40% of it actually ends up in the animal, or in the plant of question, not the animal. In this case, that's a primary productivity. So they're only 40% efficient, and this is the case of plants at best. If you took AP biology or biology, you remember your numbers a little bit. The process of cellular respiration only makes 38 ATP. All right, there's something about that 38 and that number there that really dictates where that percentage is. But we'll get into more of that as we go. All right, once again, I think this is the last one. So if you think about what's going on here, that only 40% of the energy of the 1%, only 40% of that 1%, or 0.4%, ends up in the plant, as far as in the plant's body, and they're using it for their daily lives. That being said, so if we have a producers or some type of plant, in this case looks like a grass, that's producing 10,000 J or joules of energy, that energy moves from level to level. So you have producers which produce the food or the consumable energy that, think of it as like the battery, we need this to survive. Primary consumers are herbivores, or the things that eat the things that make the food. And then there are secondary consumers which primarily are carnivorous They don't necessarily eat at the lowest possible place on the food chain. So here we have, once again, 3 organisms: grass, zebra, and a lion. If you think about from a numbers game, and you were on the savannah somewhere, you would see not many lions. There's only very, very few lions out there in comparison to the number of zebra. There's way more zebra than lions. Why? Zebra are the food for the lion in this case. There have to be more things to eat than there are things to eat them. So in this case, the lion, you couldn't have more lions than zebras because the lions would die of starvation. So they limit themselves physically based on the amount of food or energy that's available. Vice versa, the primary consumers, in this case the zebra, is limited to the number of food or the amount of food that's available for them at any given time. We have this term we call carrying capacity. So the producers are dictating how many zebra there can be. If there's too many zebra, there'll be less food because the zebra are eating more food. If there's less food, there'll be less zebras. If we carry that a step further, if there's more zebra, there can be more lions because there's more food for the lions. After a while, the numbers of zebra go down, and so will the number of lions. So there's this constant check and balance that's happening. In general, what I hope you're seeing here, there's something called the rule of 10. Every step you make from producers to primary consumer to secondary consumer, only 10% of the energy moves from one level to the next, which is a huge